Well, thank you everyone for coming to the first in what we hope to be a successful group of seminars that is organized on behalf of SIAM Activity Group on Geosciences. And just in case you did not know, SIAM is a Society for Industrial and Applied Mathematics. It has a number of activity groups, and in this case that you can check out on their website. And in this case, we are starting seminars for geosciences. It is my pleasure to introduce Marc Hesse, if you can wave, from the University of Texas at Austin. And just before I get him a chance to speak, I'd like to just briefly introduce some of the places that you might want to check out that are related to our activity group. So there is an Engage website on SIAM that has a number of announcements, as well as our geosciences group specific websites where some of these webinars will be announced, but also multiple other opportunities and activities. I would like to point out that if you are a student, then there is a way essentially for you, more likely than not, to get a free student membership, specifically if there is a student chapter at your university, or a different non-student member recommends you for admission. So if you need help with that, feel free to reach out and we'll get you going. And the benefit is that there is quite a number of announcements, both on the opportunities for workshops, career development, and opportunities for jobs that might be of interest, as well as for networking in a very wide range of engineers, scientists, mathematicians, computational and non-computational really alike. So in that sense, you might find that stimulating. And there's a next conference that is coming up. So our activity group has conference every 2 years. Next one is coming up in 2023 in June. I'm not allowed to say where just yet because we're about to sign the agreement, but the official announcement is coming up. So most likely by the next time we meet, we are going to have an official announcement. Now, this webinar series is brought to you by officers. And by the way, I forgot to introduce myself. So Inga is here somewhere hiding. She's the chair, then vice chair Vladimir Drushkin. My name is Masha Prodanovic. I'm program director, and Secretary Chris Keys is also one of the panelists here. Here we go, he's waving. So should you have any feedback, ideas, feel free to reach out. I have posted our email addresses, but we should be pretty easy to find online. And just before we start with the talk named Solutal Convection in Porous Media, I would like to point out some housekeeping. So the seminar will be recorded and it's going to be posted on SIAM YouTube page if you want to return to it, or for some reason, any other seminar you'd like to watch if you don't get a chance in person. Most of you are on the webinar side that cannot actually just speak up without help from panelists. So use Q&A part to post a question that you would like answered. I would like to suggest that we get to more serious questions at the end of the talk so that Marc can present his presentation without too much interruption. And you can also raise your hand. You can use chat just for saying hi and just for that, for chat. So if you want to socialize, may I suggest that chat is a good place for socializing. And if you want to ask a question, go to Q&A. Okay. And please pay attention to the upcoming seminars in November and December. That will be basically at the same time, second Thursdays in fall semester. So without much further ado, I would like to introduce Professor Hesse. He's a computational geoscientist and associate professor at the University of Texas at Austin. He has a wide-ranging span of degrees: geology, oceanography, fluid flow, petroleum engineering. Did I miss anything?
No, that about covers it.
And his interests are equally wide-ranging. So he is widely cited and has won plenty of awards. But I would like to highlight SciAm Geosciences Junior Scientist Prize in 2013, because that's the best one, right?
Of course.
So without further ado, Marc, take it away.
Okay, hello everybody. Well, thanks so much for joining us in this first seminar here. Let's see. So, and of course, we're making the mistake that we're not starting from the beginning.
But we know the video works, so there's that.
Yeah. So I assume you guys can see my screen.
Yes, we
can.
can.
The presentation. All right. So, well, welcome to this talk. So I'm going to talk about a topic that I enjoy greatly, and that's convection in porous media driven by solutes that change the density. And so this is a topic that I started working on during my PhD a long time ago, and it's been with me for a long time. And the interesting thing has been that it's really a topic, and I hope this comes across in the talk, where you can do this neither just computationally or just experimentally. And it's to me, it really showed me the value of both, having actual physical experiments but then also being able to query those with numerical simulations. And really only with the combination of those two approaches, I believe we were able to make some progress in understanding what's going on. This work was funded through the National Science Foundation and through the Department of Energy. And most importantly, this is of course not work that I've done by myself, but this is with a number of collaborators. So most importantly, Alex Liang, he was a PhD student that was jointly supervised between David DiCarlo and myself. And he did 5 years of hard work and produced all the experimental data that you'll see. And equally important is Bao Wen, who was a postdoc with me at the Odin Institute. And he produced all the high resolution numerical simulation of solutal convection that you'll see. Kaiwan Chang was an early PhD student of mine, and a lot of the ideas that sort of came to fruition under Alex and Bao, they kind of were seeded and started in our discussion. So I'd like to acknowledge him as well. And there's some papers that have been published. Some of the stuff that I'm presenting has been published, but actually about half probably is still in review and hopefully to be published soon. So just introduction-wise, why is there such an interest in solute-driven convection in porous media? When we started this, essentially this was all driven by interest in carbon capture and geological storage, right? And then just in case you haven't heard of this, this is the idea that you capture CO2 at point sources, transport it to a storage site, and then inject it into a geological formation for long-term storage. And the question, of course, then is immediately, what happens to the CO2? Does it stay down there? And so one idea that came up very early is that there's different kind of trapping processes that keep the CO2 in place down there. And there are hydrodynamic processes such as residual trapping, where the capillary snap-off isolates little bubbles of CO2 in the wake of a migrating CO2 plume. And that's generally referred to as residual trapping. And then, of course, there's the topic of our talk today, solubility trapping. And the key here is that CO2 is one of the most soluble gases, so it does dissolve into the water. And it's also one of the few gases that increases the density of the water. And this is spectacularly visualized here in this image. This is a Healy Shaw cell, and there's essentially a pH-sensitive dye that actually highlights the regions where the dissolved CO2 concentration has increased and hence changed the pH. And so because CO2 increases the density of the water, and because of course the CO2 vapor is buoyant and sits at the top of the reservoir, there's a potential that these plumes of dense CO2 saturated water sink away. And of course that would set up convective currents that would dissolve the CO2 faster. Last but not least, of course, the CO2 can mineralize, but that generally takes a long time. And so at the time, the question that was motivating all of this research is, what are the timescales of these different trapping mechanisms? And here's a graph from Sally Benson from the IPCC report that sort of put an educated guess on this. And so at the time, the question was really, can we quantify this better? And one thing is, Residual trapping really only acts if this plume is actively migrating. So if you inject into a reservoir that doesn't allow the CO2 to migrate, then really mostly you're looking at trapping due to CO2 dissolution. And so this then just asks a simple question, how long does it take for CO2 to dissolve in a geologic formation? And this, of course, then immediately comes to the fluid mechanics of convection in porous media. And like all good fluid mechanicists, we take what is an extremely messy, complicated, real situation, and then we simplify it, right? And so what we did and what everybody else did at the time is we in particular neglect the two-phase aspect of this whole problem. And assuming that essentially the gas or vapor phase, depending on the pressure, sits at the top of the reservoir, and then we assume that there is essentially no capillary transition zone and there's essentially a flat, immovable interface, and we just neglect the vapor phase here. And then you have a very simple problem where you're essentially just supplying a dense solute at the top, and you have a square domain, so you can use very nice spectral methods that allow you to resolve these very diffusive gradients very accurately. And then at this point, you have a very simple system, which is essentially an advection diffusion equation coupled to Darcy's law in continuity. When you non-dimensionalize this, there's really only one dimensionless number in there. It's a Rayleigh number. And you see that a Rayleigh number in a porous medium is essentially like a Peckley number, but with the buoyancy velocity, which is essentially the permeability times the density, driving density difference times gravity over porosity phi and the viscosity of the fluid. And so then the question was, how does the convective flux depend on this one parameter that this simple model has? And let's see. Okay, so here's a video. I hope you can see that. And so on the top, where it's black right now, will be the actual simulation. And on the bottom already is the answer of how the flux, so F here is the flux, evolves as a function of non-dimensional time. And what you won't see, because it's so small, is initially a diffusive boundary layer forms. And of course, diffusion gets less and less strong as you migrate further. So the flux will decline. And then there'll be a time of merging, of growth and merging of fingers. And then there's a regime of constant flux when the fingers will migrate down. And that's really the regime that we're interested in. And I'm just going to play this. And so as I say, you don't really see anything now. You can just hopefully see the fingers growing. So, and as the fingers migrate through the domain, you have a constant flux, right? And as, of course, towards the end, you saturate the domain, and then the flux has to shut down. And so what we're trying to, us and others have tried to quantify is what is this, how does this constant flux depend on the Rayleigh number? And so you can do high resolution numerical simulations. In this case, all the simulations are done by Balawen. And you can show that if you plot the dimensionless flux, and here we've non-dimensionalized the flux by the equivalent diffusive flux that you would get if you had the same concentration difference applied across the whole domain. And you see that there's a very simple linear relationship, this dimensionless flux. So you can see that the convective flux is 100 to 1,000 times bigger than the equivalent diffusive flux. And so the Sherwood number, as we call it, is just some coefficient times the Rayleigh number, okay? And you can make a very simple argument just saying that, well, I have these, we call them columnar or fingers, and, fluid there is moving down with essentially the buoyancy velocity. And so we have an advective flux that is the Darcy flux, so that's the porosity times the buoyancy velocity times whatever the concentration difference is this carries. And if I normalize this to the diffusive flux over the same domain, which is given here, and I make the ratio, which is the Sherwood number, then you realize that the Sherwood number is exactly the same as the Rayleigh number. And hence, it's not surprising that you get a linear relationship, right? And the story would have ended there if experimental studies early on hadn't given a different result, okay? And so there probably have been more studies by now, but the early one was one that I was involved in by Neufeld et al. And then one that followed up was essentially simultaneously. And both of those experimental studies seem to show that this dimensionless flux, the Sherwood number, does not increase linearly with the Rayleigh number, but with an exponent that was considered to be significantly less. And so the question was really, why is that, right? Because that would indicate that the convective dissolution process is less efficient. And why are the numerical models different from what we see in experiments? A related question is how the pattern of convection in porous media changes with the Rayleigh number. And here you see two examples. You see that as we increase the Rayleigh number from 2000 to 20,000, you see that the wavelength of the pattern gets shorter. We get many more fingers, they get narrower, they get skinnier. And so the distance between two fingers decreases, right? And you can again query this numerically. And you can see here numerical results that show that the finger spacing divided by the height of the domain as a function of Rayleigh number declines. And it's approximately 1 over the square root of the Rayleigh number. The exponent isn't 0.5, but it's very close. And again, you can make a very simple argument. You can say, well, I have this columnar exchange flow here. I have a vertical rate of solute advection. That is essentially the buoyancy flux times whatever the density difference, the concentration difference you're carrying. And the finger width is essentially half the finger spacing. And that's the rate of solute advection downward. And at some level, this needs to be balanced with the horizontal diffusion out of this finger. So this is H times the essentially diffusive flux. And the gradient is delta C over half the finger spacing. And then again, you make and in a finger that's essentially reached all the way down through the domain, these two need to be sort of in balance. And if you do that, you can show that the dimensionless finger spacing should go as 1 over the square root of the Rayleigh number, right? And here the numerical simulations don't show exactly that, but they show something very close. And so but there was no experimental data to confirm the scaling, largely because it's in all convective processes, as you increase the Rayleigh number and hence the vigor of convection, the convective structures get finer, right? So this is sort of something that people thought was kind of self-evident. So here are these two scaling laws that come out of some simple theoretical arguments and high resolution numerical simulations. And several people have worked on this. Pau was an early paper that showed these, Hewitt, Hidalgo, Slim, and many, many others, okay? What we thought is we wanted to produce more experimental data to show if this actually works. It was largely motivated by the fact that experiments seem to mismatch the scaling law for the convective flux. Okay, and so when you want to do these experiments, you have essentially two choices. You can either work with the actual gas brine system, and it turns out that's complicated because gas is compressible, because you need to be in a really sealed environment. Now it turns out that it's actually really, really interesting, and together with Todi Larsen, who's now at the Bureau of Economic Geology, and with Christian Jessen and his team at the University of Southern California, Baule has actually figured this out, how this works, how you can extract convective dissolution rates from an actual gas CO2 experiment. But that's a story for another day. So what at the time, this gas water system seemed too complicated to us and to others too. And so what we did instead is we used a single phase analog fluid system, right? And this has many advantages. You don't need, leakage is much less of a problem, no compressibility. But as you'll see, it of course introduces also some artifacts that have made this more complicated to understand. But the basic idea of the single phase analog fluid system is that you have water. So what you're looking at here is a bead pack, like 35 by 70 centimeters, roughly, about an inch thick, 2 centimeters thick, and filled with uniform beads. And initially we fill in water, so the white stuff is water. And the blue colored fluid is a mixture of methanol and ethylene glycol. And you can make different amounts of these two fluids, but the mixture is always lighter than water. And so when you pour it in after you've added the water, it will accumulate at the top of your domain. And so the interesting aspect of this analog fluid system now is that at the interface where you mix the methanol, ethylene glycol, which I'll just refer to as MEG, when you mix the MEG with the water, the mixture is denser. And I'll show you the density profiles in a little bit. And so that dense mixed fluid will sink down and it will erode the blue fluid layer from the top. I'm just going to show what this looks like. So these are the experiments that Alex did. And let's just open it up. And so this is false color in the hope that you can actually see the fingers better. So blue is the water, red is this mix solution that we've added. You can see that actually one of the biggest obstacles was here was pouring this in such a way that you have a relatively straight interface. Those are the kind of experimental difficulties that one faces. And so if you now play this, you can see a turquoise kind of color fluid forming. That is the mixture and it's dense. And you can see here on the top, you can see the time. This is about 5 minutes. So these are fairly coarse beads. It's happening fast. They sink down and you can see the red layer being eroded. And of course, we can track the area of that red layer. And with that, we have a very nice, very direct measure of the convective flux of these plumes coming down. And you can see in this little insert here that we're tracking how the area declines. And you can see that after some onset, because the interface wasn't straight, this declines very nicely linearly. Okay, and so this provides a very nice direct measurement of the convective flux. And of course, we can also just visually look at this and determine the number of fingers in this experiment. So this is 5 years of work of experimental data. Each one of these dots is repeated experiments to make sure that this is reproducible. And so here is the flux data as a function of Rayleigh number. And as we said, the theory and numerical simulations insist that there should be a linear scaling. And what you can see in the data is actually very scattered, right? Which initially was disappointing. But to first order, it sort of does the right thing. And the big surprise in these experiments that we didn't expect was actually the finger spacing pattern. So both from simple scaling arguments and from high resolution numerical simulations, we expect that if we increase the vigor of the system, convection, increase the Rayleigh number, that we would get more fingers and a smaller finger spacing, right? And instead, what we see here is that the fingers in our experiments do the exact opposite, right? So something here is completely wrong. So we don't just, like with the fluxes, we were arguing about the size of the exponent, right? Is it 1 or is it, 4/5 or 3/4? But here we have the wrong sign to the exponent. And so to me, this was fascinating and it was really interesting to figure out what's going on here. And so this was really a team effort between Alex Bowler and David DeCarlo. And so just to show you visually what this means, right? So on the top here is an experiment, again, in false color. The little insert gives you what the real image looks like. And, it's very hard to count these fingers. This was in the pre-machine learning days. Maybe nowadays this would be easier. But people will disagree on how many fingers there are, but there's clearly, let's say, more than 10. Okay, and underneath is our best attempt at a numerical simulation of this system. Well, Bowler's best attempt. And now we go, so these are small beads, so this means low permeability, small Rayleigh number. And here's an experiment in coarse beads, 3 millimeter beads, so that means high permeability, high Rayleigh number. And again, we can argue about how many fingers there are, but we can, I think, all agree that there's less than 10 and certainly less fingers than on the left side, right? And underneath, again, is our best attempt at a numerical simulation of that. And you see that in the numerical simulation, you get more finer fingers. And in the experiment, you get fewer, coarser fingers. And so something here in our understanding of pattern formation in solutal convection is backward, right? And so we were interested in understanding what's going on. And so, what is the process that everybody's, it's the elephant in the room that everybody's neglected in the theory as well as in the numerical simulations, is that diffusion is not the dominant dissipative process, right? So convection is essentially a competition between sort of density differences that drive advection and some dissipative process, diffusion, or in this case, dispersion, that wants to dilute these density differences that drive the convection, right? And everybody knows that dispersion is about 2 orders of magnitude larger than molecular diffusion for a solute. Dispersion, of course, is the process. Dispersion occurs because of the velocity variations on the pore scale around the mean flow velocity, right? The fact that two solids that were initially right next to each other could take different paths on the pore scale through the porous medium, and one moves faster because it caught higher, thicker pore throats, and the other one gets deviated, and so on and so forth. And everybody knows that this dispersion exists, right? And the question is why everybody's left it out. And the argument has always been, well, if dispersion is just 2 orders of magnitude larger than diffusion, well, then it would just shift the Rayleigh number. Instead of being 10 to the 6, now it's just 10 to the 4, but it shouldn't affect the power law, right? It might affect the coefficient, but not the exponent. And so clearly what we see, though, is that we don't just have the wrong exponent, we have the wrong sign in the exponent. And so the question is, could this be explained by mechanical dispersion? Another reason that people maybe in the convection community have stayed away from dispersion is that dispersion, of course, is a very complicated upscale process, right? And we don't have a perfect model for it. And in fact, there's a whole subfield of porous media studies where people develop extremely complicated models for dispersion that are very difficult to incorporate into a sort of standard type numerical simulation. So all of this together has kind of led to the fact that people sort of have neglected this. But clearly now we're faced with a situation where the experiments and the simulations just disagree at a level where you have to say, well, maybe we have to face this. And what are the most basic properties of mechanical dispersion? And one of the really important ones that everybody agrees on is that it is velocity dependent, right? So if you flow faster, you'll have more mechanical dispersion, right? This, of course, is a really strong negative feedback in a convective process, because if I have a really concentrated plume wanting to, migrating down with driven by a big density difference, that will also experience more dispersion, right? And so to first order, dispersion in porous media increases linearly with the velocity. And so there's a coefficient there, the dispersivity alpha, that quantifies how quickly it increases. And the other thing, and that's, in hindsight is totally obvious, but that eluded us for a while, is that dispersion, of course, depends on the grain size, right? Because it quantifies the amount that the flow path get deviated by having to go around the grain. So it is not surprising that, of course, it does depend on grain size. And for a simple granular media like the one that we have in our experiments, the dispersivity is approximately the grain diameter, okay? So in coarse media, you have more dispersion just because the beads are bigger. And then finally, of course, dispersion is anisotropic, right? It is larger by about an order of magnitude in the direction of flow than it is in the direction transverse to the flow. And it turns out that these 3 basic aspects of dispersion allow us to explain what we see in our experiments. Now, that's not the end. There are many other things, interesting aspects of dispersion, but it turns out for our purposes, we could focus just on these 3 basic ones. And if you are willing to stay with that classic model of dispersion, back in the 60s, people essentially developed a standard formulation where you essentially have a dispersion tensor that is oriented with the flow velocity. U here is actually, it's the Darcy flux. And so you have, the isotropic part is the molecular diffusion, and then the second and third term are the tensor that rotates with the flow. And just to illustrate the effect of dispersion, we have 2 images down here. These are actually, the standard solute case is what we call a one-sided convection problem. So you just supply concentration on one side, and then it doesn't really have a steady state. So this is a 2-sided problem. This is as if we, impose concentration 1 at the top, concentration 0 at the bottom. It's more like similar to thermal convection, but it has a steady state and steady profiles that you can compare. And so what you see on the left is this sort of classic columnar looking profile. And if you have good eyes or a very high resolution screen, you can hopefully see little red dots. And these are little red circles that indicate the relative size of molecular diffusion in the system. And on the right-hand side here, you see all these red ellipses. Those are the dispersion tensors. And so you can see that the dispersion tensor, for example, is velocity dependent. So here in the center of the domain, where you have the strong upflow, these ellipses are larger. And as you go towards the top boundary, there's a stagnation point there where the velocity goes to 0. You see they shrink away and become essentially pure diffusion. And so one interesting aspect of this system now is that the finger spacing is fundamentally determined by the sideways, the horizontal dissipation, in this case, dispersion, right? And so in the center of the domain where the flow is vertically upward, the horizontal dispersion is transverse dispersion. But then, of course, what happens as the flow flows up and hits the top wall, it has to turn around. And then in that boundary layer, the flow is parallel to the wall. And so what you feel here is the horizontal dispersion here is longitudinal dispersion. And although the flow near the boundary is slower than it is in the center of the domain, the fact that longitudinal dispersion is an order of magnitude larger than transverse dispersion, you actually have more horizontal dispersion here in the boundary layer than you have in the center of the domain. And that's what pushes the roots of these fingers in the boundary layer further apart than they need to be. And that's why they sort of open up in this flute-like shape. And we'll come back to this effect, and it turns out that this will be important. Okay, but first let's think about, so what is the effect that dispersion has on the pattern? And so the simplest thing, of course, is just to write down a Rayleigh number that has both the molecular diffusion and the dispersion in it. And here we've added the transverse dispersion because we thought that that is the sort of representative. And what you can then do is you can rewrite this by identifying the standard Rayleigh number, which it now has a little subscript m for molecular diffusion. And then there's a new Rayleigh number. And you see that the overall Rayleigh number is essentially a harmonic average of those two. And of course, the harmonic average is skewed to the lower of the things that are being averaged. And then we can write down these two these Rayleigh numbers. So the molecular one is just the buoyancy velocity times the height over the molecular diffusion. And in the dispersive Rayleigh number, because dispersion depends on velocity linearly, the velocity terms cancel out. And with the velocity, cancel the permeability, the viscosity, the driving density, all of those things cancel out. And all that you're left with is the height of the domain over the dispersivity, which essentially goes as the grain size, okay? And R here is the anisotropy factor, which is about 10. And so the interesting thing here is that if you look at the image on the right, we've plotted in blue, we've plotted these three Rayleigh numbers as a function of the grain size, okay? And in blue is the molecular Rayleigh number, and that through the buoyancy velocity depends on the permeability. And the permeability in a granular meter is the grain, it goes with the grain size squared. And so this blue line here has a slope of 2. Now, in contrast, this dispersive Rayleigh number depends as 1 over the bead size. And so that has a slope of -1. And so the resolution here of the conundrum is that these two Rayleigh numbers have opposite dependence on the grain size. And in fact, if we go through the simple argument for the finger spacing, where we balance the downward advective flux with the sideways diffusive loss, but we incorporate both diffusion and dispersion, then we can actually show that the finger spacing should go as 1 over the square root of this dispersive Rayleigh number. And if we plot our experiments that way, we see that it actually lines up the way we expect to. And so the interesting result here is that the convective pattern in these simple experiments is entirely independent of the standard Rayleigh number that we typically think determines the convective pattern, and it depends on this dispersive Rayleigh number that, because of the velocity dependence of dispersion, is completely independent of the usual parameters and essentially depends on the domain height and the grain size. And so this was Alex's paper in 2018. So that's the experimental paper that was published in GRL. So now that we've resolved the pattern, the sort of most conspicuous disagreement, we can return to think about what is the effect that dispersion has on the flux. And deep down, of course, at least for applications, the flux is what we care about more. And so the first thing is to just acknowledge that our Alex flux data has really quite a bit of scatter in it, right? If you've ever seen the experimental plots for, you know, the Nusselt number versus Rayleigh number for a clear fluid, you see that the data just line up beautifully. And so here is a large amount of scatter. And if you actually fit all the data as is together, you get an exponent of, you know, 3/4, right? So somewhat below 1. But if you look at the data more closely, so here I've highlighted, so we have essentially 2 knobs in our experiments. We can change the grain size, right? And with that, we of course changed the permeability, but we've now learned that we also change the amount of dispersion in the system. And we can change the driving density difference. So if here we've highlighted essentially sets of experiments where we've kept the bead size the same, but we've changed the density difference. And I'll show you in a second how we do that. Okay. And then what you can see is that essentially these data sets seem to have slopes that are larger than 1. And they're essentially sort of parallel to each other and just shifted upward, right? Similarly, if less clearly, if we color the experiments so that all the experiments that have the same driving density difference, but we change the grain size, if we color those, the pattern's a little bit more complicated and it's not really linear, okay? But if you insist on fitting a line, then you clearly get a slope that is less than 0, less than 1. And, you know, so the overall trend is just, you know, the balance of those 2. And so now let's try and understand why changing these 2 different ways of changing the Rayleigh number, right, have such a different effect. And this is where the problem in the experiments is that when you change the bead size, you're changing multiple things at a time. When we change the density difference, we're changing multiple things at a time. And the beauty of numerical simulations is that you can only change, you can sort of artificially only move one thing and keep all the other things fixed in a way that you cannot in an experiment. And this is where the simulations have turned out to be really useful. So here's the first one. So on the right here is the actual, finally, I'm showing you the actual graph of how the density of a mixture between methanol, between water, which is on the left-hand side here, and then on the right, in the different colors, are 4 different mixtures of methanol and ethylene glycol, okay? And so you can see that essentially by adjusting the amount of methanol and ethylene glycol, we can create solutions with different density, but all of them are always buoyant relative to water and form this layer against the top. And then the lines themselves track the density of the mixture if you mix one of those mixed solutions with water, right? And you see that there's a density maximum, and that's why the mixed fluid sinks away. And now the driving density difference is essentially the one between the maximum in this curve and the density of water, right? That's the density difference that drives the convective overturn. And so by playing with the composition of the MEG solution, by adjusting the relative amounts of methanol and ethylene glycol, we can change this density difference. But as you can see, we're of course also changing the entire, this whole density curve. Although they're all somewhat similar to each other, we are working with different density composition relationships in the experiments. So now what numerical experiments allow us to do, they allow us to pick one of these curves and still change the molecular Rayleigh number, right? I mean, experimentally, you could do this with a centrifuge, but we don't have a centrifuge. And so what you see is if you essentially stick to one of these density profiles, you can see that you get a very nice, let's say the blue one, a very nice linear slope, okay? And you do this, and for all of these different curves, you get nice slopes, but they're all shifted, right? So they have different coefficients. So the exponent is always 1, but the coefficient is a different one. And of course, what we do experimentally, if we try to change the Rayleigh number, molecular Rayleigh number, by changing the density difference, we have to jump between these curves. And so we're sampling across them, right? And that's what generates a trend in the experiments that is steeper than linear, right? So this turns out to, so this trend in these, where we keep the bead size fixed and just change the density difference in the experiments, this is an artifact of the particular analog fluid system that we're using here. And in that sense, we're not interested in it. And now that we know this, we can kind of subtract that out and we can correct for this. But that explains half of the story. Now, the interesting question is, how does, why, if we change the bead size, we get a sublinear trend, right? Why does the convective flux not increase as much as we would think if we increase the bead size? And now we've, of course, learned that dispersion becomes more important as we increase the grain size, right? And it begins to dominate the dissipation. So in the finest grain size, diffusion and diffusion and dispersion are sort of approximately equal. But as we go to the coarser grain sizes, dispersion becomes dominant. And again, here's something that we can't do with experiments, but we can do. So the question is, what is it about dispersion that reduces the flux? And numerically, we can now play little thought games. And so we can, in particular here, I'm showing you simulations. We're plotting the dimensionals, flux, as a function of the anisotropy of dispersion. And so we can, for example, generate a numerical simulation with dispersion, but assume the dispersion is isotropic, okay? And then we can gradually increase the anisotropy. Here, the anisotropy ratio is 10 to 1, and here it's 20 to 1, right? And what you can see, what's happening here is that the anisotropy of dispersion, and all of these are normalized in such a way that the transverse dispersion is the same. So if we're increasing the anisotropy, we're increasing the longitudinal dispersion. What's happening is the anisotropy, the increased longitudinal dispersion, is pushing the roots of these mega plumes further apart, right? Clearly, the higher. And why is that? Well, because here along the top in this diffusive boundary layer, the flow is horizontal, and we have the horizontal effective horizontal dispersion is this longitudinal dispersion, and we're making it larger by increasing the anisotropy, and that essentially wipes out these little plumes that want to form, right? And that could eventually grow into maybe one of these larger fingers. But this very high horizontal dispersion kind of kills these plumes until eventually, of course, the density of difference builds up for a big finger to form. And so what turns out is that if you look at the flux that goes down in one of these big fingers, that flux, we call them flux per megaplume, is essentially independent of the anisotropy ratio. It's always the same. But the total flux goes down simply because you have less of those big plumes, right? And so that's how the dispersion reduces the convective flux. It's the anisotropy that essentially pushes these big fingers further apart. Now, here's our best attempt at trying to simulate this. So one of Baal's big achievements is to generate this code. So we have the realistic mag density profiles. This is extremely difficult because you have a diffusive interface here where you need to resolve essentially molecular diffusion. And this interface is unfortunately moving, so this needs some mesh refinement. And then here he's added the dispersion tensor, which is very nonlinear because it depends on the actual flow velocity. And so these simulations have, although they're 2D, have burned a significant amount of time on one of our clusters. And so here's what this looks like. You can see the interface evolving. You can see the interface responding to the hydrodynamics below. And you can see that these fingers now with dispersion are coarser. And the question now is, so this is our best attempt of a simulation that has all the things that we think should be in there. And so now we can again go back to the sort of, for the moment, visual comparison between the experiments on the top in false color, and down below are direct numerical simulations without dispersion. And you see, of course, the opposite. And of course, on the left here, we have a low Rayleigh number experiment. On the right, we have a high Rayleigh number experiment. And now if we add in the dispersion, you can see it's very difficult to quantitatively compare the fingering pattern, but at least it goes the right direction, right? And you can essentially, so the knob in these simulations is the ratio of anisotropy, right? So you can scale, you can essentially adjust the number of fingers you have by playing with the anisotropy ratio. And more quantitatively, we can now, and this is really the first time that anybody's tried that, is quantitatively try to compare the convective flux as a function of the molecular Rayleigh number with between experiments and numerical simulations. And these are very high Rayleigh numbers, so these need extremely fine meshes. So in particular, this green series down here. So we've picked, and so we don't have the computational power to go all the way to the, past Rayleigh numbers of 1 million. But you can see we've picked essentially the set of experiments with the smallest driving difference, density difference, but all bead sizes. And you can see that essentially the DNS numerical simulations now reproduce this trend that is sublinear. And we've also picked the experiments with in blue with all the different density differences, but with the smallest beads. And you can see that we can also numerically reproduce this sort of superlinear trend. So I think we now have understood what's going on. So now we've kind of solved the practical problem of trying to, let me see how much, trying to reproduce these experiments, understand what's going on. And now we can indulge the question that's sort of interesting more theoretically is, what is the ultimate scaling linear if we keep the dispersion fixed, but we drive the molecular Rayleigh number towards infinity? And this has been a debate, and we'll just jump to this. So because it's a linear scaling, you can just divide the Sherwood number by the Rayleigh number, and then you're just looking at the coefficient, right? And this is this 0.017. And then Bali conducted numerical experiments where he kept, in each one of those series, he kept the dispersive Rayleigh number fixed, but then increased the molecular Rayleigh number. So the bottom axis here is the molecular Rayleigh number relative to the dispersive Rayleigh number, which turns out to be the pore-scale Peckley number, where the length scale is the grain size. And so what you can see here is that in all of these experiments that are slightly shifted, what seems to happen is if this pore-scale Peckley number is small, that means if the molecular Rayleigh number is smaller than the dispersive Rayleigh number, or at least comparable, you're close to the classic result. But then as we're pushing the molecular Rayleigh number past the dispersive Rayleigh number, there's a decrease in the flux. And that's because we're now starting, dispersion is becoming the dominant dissipative process. And we've shown that the anisotropy of dispersion reduces the dispersive flux relative to a purely molecular flux. But then that seems to bottom out. And so there's just a finite decrease in the overall efficiency of convection. And if you had a big enough centrifuge and could keep pushing the molecular Rayleigh number up and up and up, it essentially would become linear again. Okay, so that in some sense, that simple argument that we've made in the beginning that there should be a linear relationship actually holds. It's just unfortunate in our experiments, we sample this transition here. Okay, and that's why we get a sublinear trend in our experiments. But if we could do experiments at sufficiently large Rayleigh numbers with a huge centrifuge, we should be able to recover eventually a linear trend. Now, this is the numerical simulations, right? And here are the experiments. And the experiments, of course, look messy, but the blue ones, those are our smallest bead size. They cluster close to the classic line, okay, within scatter. And then if you were just to look at the green ones and the red ones, I might just be able to convince you that, maybe they've just dropped down to a new level and they're relatively constant, okay? But however, if you look at the 3 millimeter beads and the 4 millimeter beads in sort of the violet and pink colors, we have to just agree that this keeps dropping, right? And so the last question then is what's going on here? Why do our experiments disagree with these simulations that now include dispersion? And most likely the issue is that when we make the beads as large as 3 and 4 millimeters, the pore spaces are getting very large. And so here, after Bali worked with me, he went to the Bureau of Economic Geology, and there he did these really cool pore-scale simulations of solutal convection. This is 2D, right? So these are just little disks. But the benefit of these simulations is that you don't need a dispersion model, right? You're just solving Navier-Stokes on the pore scale. And you can see here nicely, here's a comparison, Darcy scale without dispersion on the left, Darcy scale with dispersion on the right, and the pore scale simulations in the middle. And you can see how we're changing the Rayleigh number here by increasing the bead size, right? And you see how the fingers get coarser. And so here, what I think is very interesting is, so here's a comparison of those three kinds of simulations in a classic Sherwood number versus Rayleigh number plot. Darcy without pore-scale, without dispersion, the blue dots, they just give you the classic line as expected. Darcy scale with dispersion shows you that, at low Rayleigh numbers, you're essentially on the classic line, and then you deviate to lower fluxes. But as we push this to higher molecular Rayleigh numbers at fixed grain size, at fixed dispersive Rayleigh number, you see the last two dots are starting to look linear again, just with a lower coefficient, right? But these pore-scale simulations, they initially track very nicely, actually surprisingly nicely, the Darcy scale simulations with dispersion to about a grain size of 1.6, right? And then at the larger grain sizes, they start to deviate markedly, and they do not recover the linear scaling as you drive the Rayleigh number up and up and up. And so why is that? And most likely, the reason is that we're getting, so here's an example of 3mm beads. You can see that you get all these very fine convective structures, essentially little plume heads within a single pore, right? And this, of course, induces tremendous amounts of additional mixing that, of course, is not captured in the classic Darcy scale dispersion model, which, of course, assumes that you sort of have a uniform linear flow, and the mixing is really due to the deviation of the flow path by the different grains. And so most likely what's going on in the experiments is that at these very large bead sizes, we get additional mixing due to convection within single pore bodies. That explains, why the experiments here do not recover this constant trend, but continue to fall off. And so with this, I thank you for your attention. And so just in summary, essentially, so this has been a many years effort in trying to understand what is going on in solute-driven convection. This was all motivated by geologic CO2 storage, but really became a study of just the physics of solute-driven convection in porous media. And as you've seen, the experiments are essential, right? Because clearly this is, if you had just looked at numerical simulations like everybody else, everything would have been hunky-dory. And it's the experiments that really pointed towards some just fundamental disagreement. But to understand what is actually going on in the experiments, and the problem with the experiments is that you always change multiple things at the same time, right? And so it's very hard to understand what is actually causing what. It's been extremely useful to have these Darcy scale simulations where we can essentially create artificial experimental series that are simply not possible in the lab. And that's allowed us to single out different processes. And then, of course, there comes a point when pore scale simulation becomes important, because you're not, so there are effects that are not Darcy scale. But in summary, we've learned that the convective pattern in these experiments is entirely controlled by dispersion. And that means by essentially domain height over grain size, right? And that's really something that I think people were not aware of before. The convective flux continues to be dominated by the Rayleigh-Darcy number, because that has the driving density difference in it. But in the presence of dispersion, this flux is lower, right? So it's lower because the anisotropy of dispersion pushes the plumes further apart. So your big flow channels, you have less of these big transport channels. And that's why the presence of dispersion reduces the convective flux. But if you indulge theoretical arguments, if you can keep essentially the amount of the dispersive Rayleigh number, and so essentially the bead size in your experiments the same, and you'd have some way of just increasing the molecular Rayleigh number with something like a centrifuge, you would find that after a certain transition, when dispersion becomes important, you should recover a linear scaling as simple theory, simple scaling arguments suggest. But this, one of the difficulties here is that if you try to increase Rayleigh numbers with big beads and things like that, you eventually run out of a situation where the continuum Darcy scale model applies. And so with this, thank you for your attention and for coming to this first webinar. I hope you've liked it, and I'm happy to take any questions.
Thank you very much. We do have some questions. So first one is posed by Soren Pop. Thanks, Marc, for the excellent, Soren, I have allowed you to talk if you want to chime in. So thanks for the excellent presentation. I might have missed it, but how do the fluid viscosity and density depend on the saline concentration? Also, do we encounter changes in the medium characteristics like permeability or porosity, for instance, with precipitation? If those properties are constant, how do the fingers form?
Okay, so it's unfair. It's like 7 questions in one. Okay, I'm not sure why there's no salinity here. We're just looking at water, and the other fluid is this mixture of methanol and ethylene glycol, right? And so how the density changes is shown here, right? So these are these nonlinear density profiles in this analog system, right? So what happened is, right, originally, of course, we're motivated by CO2 storage. So you have CO2 and a brine and all of these things. But fluid mechanicists don't want to deal with a complex system, right? And so everybody started working with these analog systems. And then these analog systems, they're very convenient, but they disagreed with simple numerical simulations, which were also simplified. And then it really became a study. It became somewhat divorced from the actual, what's going on in the actual reservoir, right? So brines, capillary fringes, all of these things. And it became really about trying to understand why these rather simple experiments to disagree, with simple scaling arguments. And so in that sense, there's no salinity here. But here's how the density difference changes with the mixture between the methanol, ethylene glycol, and the water. So the viscosity also changes, but it's a relatively small change and it's linear. And the convecting region is all to the left of the density maximum. So it's over here. And so the density changes, the viscosity maybe changes by a factor of something like 2. And this is actually the only thing that Bole didn't put in his simulator. And I've asked him, but I think he was so exhausted it was a big effort. I said, if you just add this, then we could just really claim that we have everything included. But that's this amount of work it is. But I think I do argue that it's not an important process. And so there's no precipitation, so that the medium doesn't change. How do the fingers form? Well, the fingers form because you have an unstable diffusive boundary layer at the top, right? You have the diffusive boundary layer is simply unstable, right? Let's see, where is that simulation? Can't find it. Anyway, any of these pictures, right? So it's harder, of course, to see in the experiments, but here in the simulations, you can see that at the interface, of course, you have diffusion, and so you're forming a dense layer there. And in theory, this may be stable up to a certain point, but in practice, especially here with this interface, which is not horizontal, it's pretty much always unstable.
So I think without porous medium, if you just have dense fluid on top of less dense, it's Rayleigh-Taylor instability, right? Well,
there's the classic example of just pouring a salty fluid on top of a fresh fluid, right? And then you just have this catastrophic overturn, right? And this is, at the very beginning, we're trying to relate it to this, but the dynamics of that is really quite different, right? Because what we have here is we have a buoyant fluid on top, and it's just where that buoyant fluid mixes with the water below that you form something dense, right? And this was sort of the innovation here, right? Because people had tried, and we're not the first, CO2 storage community is not the first ones that sort of interested in solute-driven convection. But it's actually been rather hard to do experiments because the obvious thing is to try and pour salt water on top of fresh water. But then you just get that mode 1, that sort of huge overturn, right? And that's not what you want. This, may be applicable in some other situations, like if you have a tsunami going over your aquifer or something like that. But that doesn't really reflect this. And so the thing that we and others, of course, thought was really neat about these analog systems is that it allowed us to simulate a buoyant fluid sitting on top of water, but continuously supplying a dense solute at whatever rate the convective overturn underneath demands.
All right. We have a next question by Chris Kuhlman, and I'm allowing you to talk, Chris, just in case you want to jump in. What effect do you think including the third dimension would have into this analog system?
because the experiments are technically, I mean, they have a third dimension, although
they do have a
small.
third dimension. Yeah, so the hope is that it's small. On a separate note, so we've got a whole like a parallel strand of investigation where we did the actual dissolution with CO2, into water, of course, in a pressure cell, which was cylindrical, so naturally 3D. And surprisingly, the 2D theory seemed to match relatively well. So I haven't followed up on the 3D studies, but I think even Powerdall 2010 already had 3D simulation results, and the numerical answer was it's still linear in the Sherwood number, but the coefficient is a slightly different one. And I'm not sure how big that difference is. So I think in terms of these experiments,
because in the 2D experiment, when the grains get really large, you have kind of almost like a boundary layer along the glass where you're watching, right?
It's sort of an interesting question. Why didn't we go to small? So what we're seeing, and this sort of has gotten lost, but this is so if you look at the picture on the right here, right? If you focus on the red beads, the red dots, right? This is the 3 millimeter beads, I believe. You see that initially it increases nicely. You go from 0.8 mil beads, 0.6, 1.6, 2 mil, right? Nice linear kind of increase. And then we went from 2 mil beads to 3 mil beads, and we had exactly the same flux. And Alex Reed did this experiment many times. And it was just kind of extremely odd to us, right? That the flux, we've just going from 2 mil beads to 3 mil beads is a huge increase in permeability, and the flux is exactly the same. And so then we kind of got desperate and said, we want another point to see if this continues or not, right? And so then we used in our desperation 4 mil beads, which of course is, rather coarse. Anyway, I mean, I think it's a legitimate question. I think it'd be interesting to do, say, simulations with a finite thickness pack. I mean, in theory, right, you could have, for example, halved, maybe for the fine beads, you could have halved the gap thickness and try to compare the full thickness to the half thickness and see if you get different results. In reality, there was enough work as is. But it's a legitimate question. But I guess my point is, to me, I feel like we've explained the main discrepancies between the simulations and the data. And as such, the model is sufficient.
Yeah, thank you.
All right, I'm going to move on to one more question. And again, so Yuhong, I am going to pose your question, but I allowed you to talk. So if you want to chime in. Thank you for the very interesting talk. Would you share your idea on the macroscopic description of the mechanical dispersion, which could be incorporated into field scale reservoir simulator? What are the main challenges to be addressed?
Well, so that's a whole different bag of worms altogether. So the first thing, and this I haven't highlighted this, right? So when we, when Alex wrote his paper, and we sent it to GRL, and we wrote it kind of more like a fluid mechanics paper, and then they said, well, you have to apply this to geologic thing, right? And you find out that even in Sleipner, which I think of as a rather coarse, very permeable kind of system, the grain size is much smaller than it is in our experiments. And so then you're actually back in the domain where actually molecular diffusion, dispersion actually isn't dominant. Now, which, was sort of kind of a difficult sell at the time. But of course, in a realistic medium that's heterogeneous, you have, the terminology is, I'm not up on the terminology for how but you have sort of macro dispersion, right? You have dispersion that comes about due to the fact that your real medium is heterogeneous, but you're not resolving the heterogeneity, and you're simulating, your blocks are just too big, And so how you incorporate that kind of additional mixing or dispersion that is due to unresolved heterogeneities, I think is quite different, right? I mean, this for potentially anyway, from the dispersion that we have here, although I guess in some sense, you know, you have to flow around low permeability regions. So I've never really had to investigate that, but just by the fact that, of course, it must depend highly on the geologic structure. I'm sure there's, you know, there's a whole field out there of people that are trying to understand this. I guess the one thing that I would expect for some sort of a layered system is that there is an anisotropy, but it be less dependent on the flow direction and more sort of, you know, horizontal versus vertical. And that might actually suggest then that you have a similar effect that you push the plumes further apart. But yeah, I haven't investigated that. I think it's clearly in the context of trying to actually apply this on a field scale, this is clearly important.
Johan, does that?
Thanks, Marc. Yeah, because some paper have actually talked about this, and they are saying that actually the numerical simulations for short of capturing the field observations, and I'm wondering this might be one of the reasons that the discrepancies occur, and we might be able to sort of improve the accuracy of the model by incorporating such dispersion. Yeah, but thank you. Yeah, that's a very nice talk.
Thanks.
All right. I would like to be respectful of everybody's time, but Marc, are you okay with one more question?
Yeah. No,
I also don't want to stop the flow.
I'm not offended if people drop off. I have definitely 10 minutes more. You know.
All right. So Keita
if I fall off my
Yoshioka,
chair, then I guess it's over.
all right. Keita Yoshioka has the question: in the pore-scale simulation, the distance gap between the grains seems constant. How was this distance chosen?
Yeah, that's a very good question. So I think clearly the porosity has to be the same. So, you know, I'm not sure if Paula is in the audience, but
yeah, I think we lost.
but you know, clearly, you know, the porosity has to be constant, and so I think, you know, and it's clearly a regular pattern. So I think if porosity is constant, then then you can calculate how this needs to change. I'm not sure if the gap is the same. I guess it is, right? It just scales. Yeah. So sorry. No, the gap. I mean, the pattern's always the same, right? And I think the gap width grows with the beads. That's what I assume. That way you keep the porosity the same, right? You just take the whole thing and you just, you know, scale it. I have to check that though.
All right. Well, thank you. This was excellent. And thanks everybody for showing up for this first webinar. Keep your eye for the November one, which is going to be again second Thursday in November at the same time. Marc, thanks again. It was a pleasure.
It's been a pleasure. Thanks so much.
Thank you.
Thanks, Marc.